Hi everyone, welcome to the Learning Curve, Scale AI's weekly Tech Talk series. Today's topic is model-in-the-loop data curation. Before we begin, just a few housekeeping notes. This webinar is being recorded and we will send you the recording via email. We will have a Q&A after the presentation, but if you have any questions as we go through the presentation, please submit them using the Q&A feature in the Zoom. Lastly, we will be sending a survey in the Zoom chat. Please complete it post-webinar. And with that, Sasha, please go ahead and take it away.
Thanks for the introduction, Hannah. Welcome, everybody. My name's Sasha, and I'm a software engineer here at Scale. To give you a bit more background about myself, prior to joining Scale, I graduated with a master's degree in computer science from Stanford University, where my concentration was in AI. And since joining Scale, I've been working on the Nucleus team, which is the dataset management platform for machine learning engineers. And a lot of the problems that I work on every day at Nucleus have motivated the ideas behind this tech talk. So the focus of this presentation will be how model-in-the-loop data curation can help machine learning teams tackle the challenge of long-tail distributions. So to get started, what is a long-tail distribution and why should we care? In simple terms, a long-tail distribution is one in which there are a few common categories, followed by many rare categories. Take, for example, internet search terms. There are several keywords that are extremely common, like the weather or the Dow Jones average, that get queried millions of times per month. And then there are a bunch of other queries that are relatively rare or localized. So for example, there are only a handful of people Google searching when the local tennis court opens in the morning. So as a developer working on search relevance, it might be tempting to ignore the long tail, the orange region of this graph, in order to focus on the more common cases. But the deceptive thing about long tail distributions is that the tail typically makes up a large portion of the probability density function. So this graph is exaggerated to make it more readable, but in reality, 70% of the PDF falls in the tail region, and so it's impossible to ignore. Long-tail distributions are significant because they occur often in the natural world. So for example, the frequency of English words is long-tailed, as is the visual taxonomy of the world. And this is significant to deep learning practitioners because deep learning algorithms tend to generalize very poorly to examples that aren't adequately represented during test time. So I usually think of deep learning as a subset of supervised learning methods. And something that's generally true of supervised learning methods is as the frequency of a particular category decreases in the training data set, so does the average model accuracy on that category during test time. And so as a deep learning engineer thinking about model performance on edge cases, it's actually really hard to get adequate model performance on something that occurs very rarely in the training data set. Let's consider a specific example. So here I've pulled up the class distribution of the Berkeley Deep Drive dataset, which is an open source image dataset targeted at autonomous vehicle applications. And as you can see from this class distribution, it's somewhat long-tailed. So cars occur very frequently. There are about 8,000 car annotations total. But as you move to the right of the graphic, other objects of interest, such as people, trucks, buses, and bikes, occur relatively infrequently. And so if I were to train an object detection model on this dataset, I would expect predictions on the bicycle class pretty bad. I actually went and conducted this experiment and trained a standard object detection architecture on Berkeley Deep Drive. And when I pulled up bicycle predictions, that's exactly what I saw, right? In the scenario, I correctly identified a cyclist. The localization of the box is somewhat poor. And additionally, there are a lot of false negatives and false positives. So if I were an engineer at an autonomous vehicle team and I was working on a perception algorithm, this is really a rare edge case where I would want to improve model performance. And that's really where the art and science of machine learning engineering come into play, right? There are a lot of different ways to try and improve model performance, whether that's trying new architectures or investing more time in hyperparameter tuning. But the only way to target model performance on this particular rare scenario is to add more examples of this scenario to your training data set. So that's my actual advice. If I were to give an actionable recommendation for how to remedy this particular failure case, I would say simply find more examples of this cyclist class and add it to your training data set before your next experiment. That example brings me to a larger point, which is that taming the long tail is really expensive. Ultimately, developing an AI product can be thought of as a process of iterative experimentation. And it's usually the case that once you address one long tail failure case, it feels like 2 or 3 more crop up in its place. To make matters worse, deep learning experiments also tend to get more expensive over time. They exhibit a phenomenon called diseconomies of scale. Basically, what that means is that as model performance improves over time, the marginal cost of that improvement increases exponentially. So to go from 60 to 65% accuracy, you might need an additional 10% of training data. But to go from 90 to 95% accuracy, you might need to 10x the size of your training data set. The threat model here is that in the quest to tame the long tail and create robust and performant model predictions, even on rare scenarios, machine learning engineers get caught in an endless loop of experimentation. So what can we as machine learning practitioners really do about this? Obviously, the process of experimentation isn't going to go away anytime soon. And so to me, one logical thing to concentrate on is how can we make each experiment as efficient and targeted as possible. If we think back to my earlier point, that the best way to improve model performance on a specific scenario is to identify more examples of that scenario to expose during training time, then in this flowchart, it's the data curation step that is most critically overlooked. So the approach that I'm advocating here is kind of a data-centric view on deep learning experimentation, where for each training routine, you identify a model failure case and find additional training examples to prevent future failures on that case. That's really what I mean when I talk about model in the loop data curation, that you can think of building an effective training data set as simply a process of mining the long tail. To back that up a little, Scale started as a data annotation company. And ultimately, we decided to build Nucleus because customers kept asking us, which data should we label next? And if you take away anything from today's presentation, you should take away that randomly subsampling data is a horribly inefficient way to construct a training data set. And so it's typically the case that teams that are building proprietary data sets collect a lot more unlabeled data than they're able to actually train on. And so the natural question becomes, how do you select the images to include in your training data set? I took this graphic here from an NVIDIA AI blog post that also targets data selection. And the point here is that the image in the top left corner is a typical highway driving scene, whereas the image in the bottom right corner is a person wearing stilts crossing the street. The value of these examples is very different, right? The highway driving scene is probably already adequately represented in a training data set, whereas the person on stilts is a great example of something where you wouldn't want this example to fall through the cracks because of a random sampling approach. So if a machine learning team wanted to adopt this data-centric view on experimentation, they would need 3 key capabilities. The first is to be able to diagnose qualitative failure cases. And what I mean by this is moving away from characterizing model performance with respect to a summary metric like accuracy or loss or mean average precision, but instead being able to say, a pattern I see in my model's failures is that it does a poor job detecting cyclists at nighttime. Intuition behind this is that for me as a machine learning engineer, it's much more actionable to know I do badly on cyclists at nighttime than it is to know that my model currently achieves 90% accuracy, because I really want to know what the areas of improvement are. The second step is that once you've identified this failure case, you want to find more examples of this scenario in your unlabeled data set. And of course, that's easier said than done because by nature, unlabeled data is difficult to search over. And lastly, once you've identified a failure case and taken steps to remedy it, You want to monitor this case to ensure that your model doesn't regress in the future. To make this a bit more concrete, I thought I'd walk through how we approach this type of model in the loop data curation workflow within the Nucleus platform. So here I'm on the Nucleus home screen, and you can see I have multiple data sets uploaded, but I'll click into Berkeley Deep Drive to continue with our previous example. So imagine that I'm a machine learning engineer at an autonomous vehicle company, and there's been a bug report that our QA drivers are having to intervene frequently in scenes that involve trucks at nighttime. And so I've been assigned to look into this problem. I might start by clicking into Insights and getting a high-level overview of what's contained in my dataset. This is the same distribution that we saw earlier. We can see cars occur very frequently, but there are only about 35,000 truck examples in our dataset. The first question I would ask myself is whether trucks is a very rare edge case, but it looks like we have enough information to work with here. So I can actually click through that chart and narrow down my search results to just images containing at least one instance of a truck. And so already I've narrowed down my data set to a subset more relevant to my current inquiry. But I have a bit more information that this problem only surfaces at night. And so a cool thing about the Nucleus query bar is that it's very flexible, and we actually have the ability to search over any user-defined metadata. So here I'll narrow my metadata down to just trucks or just images recorded at nighttime. Okay, so now I've narrowed it down to the subset of interest. And the next thing I want to do is visualize my model performance for the particular model in question. Nucleus is a developer-first product that's built on top of a set of public APIs. So it takes just a couple lines of code to upload your model predictions to the platform. Once model predictions are uploaded, I can choose which model I'm interested in looking at from a drop-down menu. And here I'm visualizing my model predictions in red alongside the ground truth. So already this is a pretty powerful qualitative debugging workflow in that if I'm a machine learning engineer and I'm just getting started with this particular problem, I probably just want to see a lot of examples of my predictions in this particular case to see if I can identify any patterns. But Nucleus supports more quantitatively driven workflows as well. So here I can change my view to patches view, which instead of viewing my predictions at the image level, I can crop each image to view model predictions individually. And once I'm viewing model predictions individually, I can sort them by performance metrics. So in this case, IOU is a common performance metric used for object detection applications, where IOU essentially quantifies how well two bounding boxes overlap with each other. And so you can see here that when I sort by worst IOU, I get the most egregious mistakes that my model made. And indeed, I would say that they're pretty bad, right? So I have a person prediction floating in the middle of the street here and a car prediction floating in the middle of the sky. And that's definitely a case that I would want to remedy. We've more or less talked about how to conduct debugging workflows with the Nucleus, but we haven't quite addressed the data curation part yet. And so in order to talk about data curation, let's start from scratch and look at a new example. Now imagine that there's a different bug report saying that we've had a lot of false positives with the traffic light class in particular. How would I go about fixing that type of model failure? Well, in this case, since the problem is with predictions, I would probably want to start by looking at images where I've got at least one traffic light prediction. And since we're looking at false positive, let's pull up a set of images where we've got quite a lot of traffic lights. So when we look at the first couple search results, we see that those definitely make sense. These are indeed scenes that contain a lot of traffic lights. But if we scroll down, we might find some interesting edge cases. So here's an image that I was looking at earlier today, where the sirens on the police car were mispredicted as traffic lights. So that's the type of model failure that definitely makes sense in that those objects are visibly similar, but something that could really have a big impact on the performance of a vehicle at test time. You really don't want to have false positives in a traffic light class. So now we have a problem that we've identified sirens on police cars as an interesting edge case, but police cars aren't present in our dataset taxonomy. So it's really difficult to discover more examples of police cars when they're not explicitly labeled and we can't search them in the search bar. And so in order to find more examples like this, we'll have to rely on a visual search tool that basically brings up visually similar images. And this type of method is incredibly powerful because it doesn't depend on any ground truth labels being present. And so basically, we extract feature descriptors from the raw pixels of an image and then build a search engine over those feature descriptors. Now that we've done visual search, we can see that we've surfaced some relevant examples in the similarity results. And so I could go through these images, manually select them, and export them to a slice to revisit later on. But that's a pretty manual process, and this is something I expect to repeat many times during my experimentation. And so what I would really like to do is take this edge case and pull it into the explicit taxonomy of my data set. In order to do this, Nucleus supports a feature called auto tag. Basically, what auto tag does is it learns to characterize a particular edge case and then applies a tag for this edge case as structured metadata over the entirety of the data set, both images that exist now and that are uploaded in the future. The first step here is to create a name for my auto tag. Let's call it police cars version 1. And when I click next, I get results that based on those 2 seed images, what other images might be considered part of this class. So one way that auto tag differs from the visual search feature is that it provides this opportunity for human in the loop feedback, where I can correct the model predictions to hopefully refine them over time. So here I'll take a moment to select the images that are all correct predictions and actually contain a police car, which is the class of interest. And so now, in a subsequent refinement step, we can see that the model predictions have become a lot more relevant. So when I finish creating the auto tag, in the background, this metadata field, police cars version 1, is applied to all images that the model predicts will be part of this rare scenario. And so when I go back to the homepage, these auto tags persist between sessions, and I can actually search on them explicitly in the search bar. And so using this functionality, I'm able to curate and revisit rare edge cases of interest, and for example, send them to labeling later on. And so if I were interested in prioritizing unlabeled examples to label next, I might intersect my auto tag query with a query over annotations to limit the results to just those that haven't been annotated yet. So that's how we on the Nucleus team think of supporting a model in the loop data curation workflow, where you first identify failure cases in your model and then design some marginal dataset examples to try and address that failure case. So I want to finish things off by saying I think it's becoming a lot more common for people in industry to talk about constructing training data sets intelligently. So this is a quote from the head of AI and ML at Cruise from Scale's recent conference, talking about adopting a model in the loop workflow to make sure that you're learning from mistakes found in previous experiments. So there are a lot of different terms that relate to this concept of building data sets relative to model outputs, whether that's active learning, continuous learning, or model in the loop curation. But the ultimate idea is that not all data is created equal, and you really want to be including training data points that are going to have the maximum lift for your model performance. And I'm happy to answer any questions.
Great, thank you so much, Sasha. All right, now we have some time for Q&A. So the first question I have for you is, you mentioned how dataset balance and long tail classes impact model performance. Can you talk a bit more how data quality affects model performance?
Yeah, definitely, Hannah. This presentation was really targeted at how is model performance affected on cases where they just don't occur very frequently in the training data set. But just as kind of having a very underrepresented case will lead to model failures, having poor training data set quality will also lead to model failures. And so the kind of qualitative debugging workflow that I was demoing in Nucleus also pertains to finding issues with existing labels. So for example, sorting by false positives in a model run might reveal that, labelers were supposed to annotate police cars, but maybe they miss a police car every once in a while. Kind of examining the regions of your data set where there's disagreement between ground truth annotations and model predictions both uncovers issues with the model and issues with the data set.
Great, thank you. Can you talk more details regarding this similarity search engine?
Yeah, definitely. And so, kind of as I was saying previously, one of the core capabilities for an AI team that's interested in adopting this data-centric view of experimentation is being able to source similar images from unlabeled data, right? And that's a difficult engineering problem to solve because unlabeled data is inherently unstructured and difficult to search over. So the approach that our search engine takes is that create feature descriptors for images based on the raw pixels alone. And so those feature descriptors are not dependent on any ground truth annotations being present, which is how it is that they work on unlabeled data, and then essentially build search functionality over those descriptors. But I can't give any more detail than that.
How does the auto tag system identify similar images to seed images?
Yeah, definitely. It's very related to the similarity search feature, right? In that it's feature descriptor dependent. But you can think of the auto tag feature as building a binary classifier, one that predicts whether an image is or is not part of the scenario.
If the police light was a rare case scenario, what about some other visually different vehicles? How often does the model have to be updated to include new exceptions?
Yeah, definitely. I think one of the difficulties of long tail distributions, right, is that it feels like the rare edge cases are never ending, right? So you might see in an initial experiment a model fails for cyclists at night. You might resolve that issue, only to find, for example, the person crossing the street on stilts, in which case, that truly is the mother of all edge cases. You maybe only have one of those in your training data set. I think the reason that we believe in kind of this human in the loop approach to sourcing edge cases, as opposed to completely automating this process, right, is that you as an engineer or as somebody on a machine learning team more broadly has a really good kind of filter / idea of what failure cases are actually really relevant to performance out in the real world, right? Because ultimately, long tail distributions exist because it's our attempt at taxonomizing the complexity of the real world.
Great. The next question I have is, model in the loop implies my model is used for selection. This is not quite the case here, right? Instead, it identifies failures from validation, but requires human interaction. Is the model's embedding used anywhere within that process?
Yeah, definitely. So one feature in the Nucleus product that wasn't featured as much in the kind of demo section of this talk is the quantitative model debugging workflows, where basically what you saw was a grid view where you can visualize model predictions and how they intersect with ground truth. We also have a separate view called a patches view that shows model predictions one at a time, as opposed to aggregated on a per image basis. And within patches view, you can sort by worst IOU, which is common evaluation metric for object detection algorithms. IOU basically quantifies how well a predicted bounding box overlaps with a ground truth bounding box. One of the core ideas here behind diagnosing model failures with Nucleus is that you can use this worst IOU sorting mechanism to automatically surface all of the objects that gave your model the most difficulty. Kind of the hypothesis behind all of this, right, is that surfacing those examples where the model did the worst is a very kind of repeatable way to diagnose these qualitative model failures.
Great. Regarding selecting database learned mistakes from the perspective of having automation instead of manual process, are there any quantitative metrics or is it a learning-based method?
Okay, so if I'm interpreting this question correctly, I believe what this person is asking, right, is that what we showed here is a very human in the loop workflow, right, where you had to come to the conclusion that I was doing badly on police cars, and then found more examples that way, right? So how can you completely automate this workflow? So I think that active learning, for example, is the field of deep learning research that really addresses this overall problem formulation of I want to select examples to add to my training data set. And I think active learning is a perfectly reasonable way to approach this type of problem, but there probably is still some value to having human in the loop workflows as well. So that's what I would recommend if you're interested in exploring completely automated methods for this. I would recommend digging into that literature.
Great. The next question I have for you is, are you supporting both image level similarity and object level similarity?
Yeah, that's a good question. As I mentioned before, the feature descriptors are computed on an image level. What that means is it's grouping images based on how they're visually similar over the granularity of the image as a whole. And one use case in which that breaks down is when the particular object you're looking to source more examples of occurs on a relatively small area relative to the entire image. So a concrete example there is that an image-based feature descriptor would do really well, like given an image at daytime, to find similar images during the daytime. But if you were trying to find cyclists between the night and the day, those images differ with respect to time of day in a way that might make the descriptors far apart. So Nucleus actually supports the auto tag feature on a per object level as well, where the same basic principle applies, but you're kind of generating a representation of each object instead of just each image globally.
Great. What kind of effect does dataset size have on edge cases? Number of edge case images that I have to find for solving the edge case, is it a function of my training dataset size?
Yeah, that's a really good question. So I think it does, to a degree, depend on the taxonomy of the data set, right? And ultimately, what the end goal of this AI model in production is. So I can definitely see how an approach to AI modeling that's just trying to wrangle the real world, something like an autonomous vehicle use case, right? That indeed, if you committed to labeling every object encountered in every image, the number of classes would explode, but it doesn't necessarily have to. And so it's kind of a design decision with respect to that modeling exercise, whether you want to explicitly label and kind of make automated decisions based on whether birds occur in this image or whether cats occurred in this image or really cyclists. So to me, kind of the number of edge cases is really a subjective question that comes down to what the engineering goals of this particular model are.
Great. What if we don't have enough edge cases? Can we improve model performance with small amount of less noisy data?
Yeah, that's certainly true. So Scale actually published a blog post about this recently, kind of doing a whole experimentation loop in Nucleus on a small data set and testing how dataset noise affects the results. And the results that we found anecdotally there, where we were training on a data set of 200 images, is that label noise does really make a difference, especially when the size of the training data set is small. And so usually, I guess, if you assume that noise is normally distributed, as you get more images, kind of it cancels itself out because the mean is zero, assuming that that's true. But regardless, kind of I would say dataset noise tends to make model performance suffer the most when dataset size is small, but it does pose a problem, or improving label quality can be a way to improve model performance regardless of what your training data size is.
Great. With Nucleus, can you specify a region of interest in the original image when setting up an auto tag? For example, draw a bounding box around the police car to specify that that's the target for visual similarity?
Yeah, that's a really good question. Yes, with the object level auto tag feature I was describing earlier, you can specify a region of interest exactly in the way the question described.
Great. This is just a visual representation, meaning mostly through images, but what about some plots or matrix of GT versus my model?
Yeah, That's a good question. Didn't show it off in that demo, but Nucleus does have a feature called the Insights page that kind of renders or visualizes aggregate metrics across a data set, including like distributions, distribution charts of different classes, and confusion matrices. I encourage you, it's publicly available. You can go look at it and explore that confusion matrix feature in your own time.
Great. Are you supporting any NLP use cases?
Yeah, that's a good question. The platform is focused on computer vision and 3D applications currently, but we do support document transcription use cases. So optical character recognition is kind of an interesting crossover between NLP tasks and computer vision applications. So if you're interested in using it for NLP tasks, definitely consider reaching out. We'd be interested to talk to you about what your exact needs would be.
Great. What's the time complexity of finding similar images given an input example?
Yeah, that demo that I showed with the police car actually happened in real time at the time granularity of an individual HTTP request.
Great. How does one go about finding failure cases in a structured way using Nucleus? The police car traffic light example just happened to be at the top of the dashboard.
Yeah, definitely. Let me see if I can actually pull it up here. Give me 1 second. Okay, so here I am on the Nucleus homepage. And the view I was mentioning earlier for quantitative debugging workflows is located over here, the patches view. And so when we click into the patches view, each image is cropped down to the level of an individual object, which is really useful for making sense of predictions when they all overlap with each other. And so here you can see that I have some pretty awful predictions. So for example, this traffic light does not localize well at all, and same here. And so sorting by worst IOU, as mentioned previously, is a really good way to surface issues in the current model. And the overall model we're looking at here is not particularly performant, but we can toggle between different model outputs. And so, for example, flipping over here and then also navigating over to false positives, we can get a lot of interesting insights about dataset quality. So this view usually shows a lot of missing annotations. This is a really great example that in this case, the model run predicted a car, and in our kind of automatic model evaluation metrics, it got interpreted as a false positive because there's no matching ground truth. But if we click in here, we can see that actually what happened is this image is missing annotations. And so kind of the model failure is actually a data set failure. And so that's a really good way to go about debugging those issues. I hope that helps. So kind of the way I envision it playing out is you have a new experiment, you know that you have 90% accuracy. So naturally you're interested in examining those images, the 10% where the model failed. And then maybe you're able to find some patterns simply by looking through a lot of examples of misclassifications.
Great. The next question I have for you is how much pre-compute is required for data sets? For example, descriptor computation and indexing.
Yeah, that's a good question. A fair amount of that is computed in advance by our system automatically. And we also support users uploading their own feature descriptors. So that can be a really good way. Kind of ours are designed by design to be very generalizable across different data distributions. They're not just autonomous vehicle cases, but maybe something more general, like think about object classes in MS Coco as an example. But if you're interested in having that similarity search be really targeted at a particular model, users can always upload their own.
Great. How would you compare this model in the loop workflow to other data selection methods like active learning?
Yeah, definitely. So we touched on this a bit previously. Somebody asked about completely automating data selection. And I would say both are viable methods, and it depends on what your goals are. So active learning, for example, does really well overall at targeting, picking annotations relative to where current model failures are. But active learning selection processes sometimes falter with respect to the diversity of items chosen. And I think in practice, it can take a lot of engineering lift to get machine learning experimentation automated enough that continuous training is possible. And so that's something that we're actually really interested in supporting within Nucleus in the future, right? Is kind of getting increasingly intelligent about how we automate and support automation for these types of data set curation workflows.
Great. Can customers deploy Nucleus on-premise?
Yeah, that's a good question. Not yet, but we are looking into releasing privacy mode for Nucleus, where basically customers can upload their data without having that data accessible to scale. So basically leveraging the entire platform and full set of features without loosening the permissions on those individual assets.
Great. What would you say to someone who didn't agree with the idea that the best way to improve model performance is to focus on the data set?
Yeah, that's a really good question. And I would say it's not necessarily the case that I completely disagree with that person. I definitely think of machine learning engineering as an art to a certain degree. And so, of course, right, when you study AI, for example, right, there are a lot of different ways to go about improving model performance, whether that be, trying new architectures, hyperparameter tuning, data augmentation, right? All of those methods definitely have their place. I think the reason that I really believe in the data curation aspect is I think overall within the deep learning community, there's too much emphasis on the model work and not enough emphasis on the data work, right? And so model failures, I think of as a combination of deep learning models failing to learn a probabilistic representation of some concept, right? And that failure to learn that probabilistic representation, right, has as much to do with the data set the model is learning from as it does with the model architecture itself. So I think in reality, those two things go hand in hand. And the reason I'm emphasizing this data set centric approach is I think that that's not emphasized enough in public discourse.
All right. I'm not seeing any more questions. So thank you so much for joining us today. In terms of next steps, we will be sending you an email with the recording. Please tell us what you thought of our talk in this. The survey link should be sent in the Zoom chat. And lastly, our next tech talk is scaling up document processing on June 23rd. You can find all the information for the event on scale.com/events. Sasha, thank you so much for your time today. And thank you everybody for joining us. Have a great day.
Thank you.